Good afternoon. Today we'll be discussing the recovery efforts of Indonesian moth species. I'm Danielle Deming and I represent the Invertebrate Alliance of Southeast Asia, a nonprofit that focuses on invertebrate conservation in Southeast Asia, like Indonesia. We've partnered with the Indonesian Ministry of Environment and Forestry for these efforts. The ISA has four main objectives to complete its mission, being protect native habitat, promote research, provide education and outreach, and seek partnerships for conservation. Some background on the project. We've surveyed 5 islands for moth species abundance and diversity, and these 5 islands are the last with forested habitat in the region. We've evaluated the data so we could determine priority protection for each of the island with the funding resources that we have so we can better implement an effective conservation management plan. So moths are really interesting. There are actually 10,000 species of moths in Indonesia alone. They are nocturnal and their diet comprises of nectar and plants, and they live in variable habitat from dense forested area to urban. They are pollinators and considered ecological indicators of environmental degradation. Moths are affected by the minute changes in climate and show changes in reproduction, mortality, dispersion, and development. Moths, being a functionally important and huge diverse group, can be used as a potential bioindicator of the group in present scenario of environmental degradation in areas from open areas and forest patches. Moths as ecological indicators are established globally, covering a wide range of environmental issues like habitat fragmentation, climate changes, and deforestation. For our methods, we used RStudio to answer our quantitative questions, and this graphic shows the islands in question. As you see, Island 5 is the smallest and most furthest away, with Island 1 being the largest, and Islands 1, 2, 3, and 4 being the closest in proximity. Here's our methods table, what we use for species richness and individuals per island, as well as our diversity indices. We use the Shannon's as it is most common. However, it's the most sensitive to rarity. So we did also use a Simpson's index for better comparison. For evenness, we use J-evenness as it's sensitive to rare taxa and high sample size. We had a Weibull relationship for a species area relationship, and to account for these differences in size, we did rarefy to make it a more equitable comparison. For a similarity, we use a Bray-Curtis dissimilarity because we have a lot of zeros in our data set, and it treats high and low values equally, which is important when comparing different size data sets from each island. So let's look at some results. Island 1 had 20 species, with the rest as follows, with an overall of 22 species, and Island 1 being the most speciose. For individuals, we did have a high number of individuals in Island 1, with an overall of almost 2,000 encountered, Island 1 being the most individuals per island, and Island 5 being the least. For our diversity indices, our first table being the Shannon Index, we found that Island 1 is the most diverse, and our Simpson's Index also shows us Island 1 is the most diverse. It's important to note that Island 3 being the second most diverse and Island 5 being the least. When looking at evenness, the table shows us that Island 1 is the most even, and Island 2, interesting enough, being the second most even, with Island 5 being the least. So in summary, the table shows below all of our results here. And we see again that Island 1 is the most speciose, diverse, and even. When looking at the species area relationship, we did find that species richness did increase with area in a logarithmic fashion as shown in the graph below. We used this to make it more linear to better fit the data. It's still not a great fit, so we did perform a multi-model average. See here that the logarithmic being in that middle range, with the highlighted green being the most powerful. And we see that the Weibull 4 was the line of best fit for our data. For our assemblage, we see an exponential relationship between species richness and area, but then it plateaus at about 50 square kilometers. When considering diversity patterns, we do sit at about 6 degrees latitude, so this coincides with the latitudinal gradient idea that higher biodiversity is closer to the equator when comparing focus islands to temperate and Arctic islands. And as talked about previously, the species area relationships we find does support that more area supports more species, and larger islands experience a higher species richness than smaller. For our abundance patterns, we encountered a handful of species in high abundance. Plutitoides, Flavinescens, Rhizobia beckii, and Tochiera liviaceae being the highest. And of those, Plutitoides flavescens, Tochiera liviaceae, and Sericula trivenestrata were on 4 of the 5 islands. However, no species were found on every island. For distinctive species, 9 species were only found on 1 island, 2 of the asterisks being Island 5 and the only species found on that island. This supports that more species are rare and few are common, and also common species are widespread and rare restrictive. Again, remember that Island 5 being the smallest and most furthest away. Some environmental factors to consider. This is a preliminary management tactic. We are assuming that all of these islands are similar in habitat quality, so we need to assess forest density, temperature, available forage, and refugia for future analysis. When comparing these islands, it's important to verify the data so we can measure them equitably. And as we see, Island 5 is the only island predicted to have accurate species. This means that 1 through 4 are severely underestimated. When we look at the refraction curve, Island 2, 4, and 5 reach their asymptote with a lower number of individuals, whereas 3 and 1 are much higher, 1 being as close to 1,400 individuals. This does cause difficulty in comparing islands fairly. However, the islands with the highest biodiversity were still the most underestimated, so the context is still the same. When looking at similarity, we use the Bray-Curtis similarity table, and here are the results. We see that Island 5 is the most dissimilar or most unlike the rest. And as we mentioned before, only 2 species were found and they weren't found anywhere else. Islands 2 and 4 were the most similar overall with that lower value. And 1 and 3 are also very alike. Islands 2 and 4 were the most dissimilar in the island cluster, and it's important to note that species found on 2 and 4 were also found on 1 and 3. Island 1 has 7 species not found anywhere else, and 1 and 3 shares 10 species that aren't found anywhere else. So we'd like to implement some management recommendations. So our objective is to buy the islands to create nature preserves with a budget of 475 million rupiah with the priority ranking method. As you see in the table here, we cannot buy all the land as that would cost 552 million. So we'd like to show the results again and justify our recommendations. So first, we'd like to procure Island 1 as it is the highest in richness and evenness and also has the highest diversity scores. Island 1 is our first priority and it's also the largest in size, so it will take the largest chunk of money. This leaves us with 199 million rupiah. Our second island of recommendation would be Island 3 because it's the second in size and biodiversity. Remember that these islands were both severely underestimated according to our analysis, so another important reason to protect them. The hope is that by protecting these two, Islands 2 and 4 species may disperse to Islands 1 and 3, following the MacArthur-Wilson's island biogeography, where clustered islands may provide a retreat for dispersal inclined species. That leaves us with 79 million rupiah. So lastly, we'll buy Island 5, as it has the lowest in richness and lowest population and has endemic species not found on any other island. We would have 55 million rupiah left, so not enough to purchase more. Some considerations moving forward, we need to measure habitat quality now that we've grasped quantity. We also need to determine negative impacts like invasive species, anthropogenic aspects, agriculture development, and we like to mitigate those with education and outreach. Culturally, Indonesia has 300 ethnic groups, all with their own set of customs, so finding balance in these customs with management is critical. I'd also like to recommend using the 55 million rupiah left over to create smaller conservation easements throughout the archipelago in areas where habitat is ideal for biodiversity, as well as protecting water resources for people's agriculture and living needs. We would need to observe where these areas may be, which we can do partnering with the ministry. And protecting these areas will also promote ecotourism, which is a major economy aspect of Indonesia. The benefit of protecting natural areas goes beyond species biodiversity and promotes the sustainability of these areas economically. So, some final thoughts. So in summary, I'd like to implement land procurement for Islands 1, 3, and 5. And today we were prioritizing biodiversity and uniqueness, so we're protecting what we have, but restoration could be considered at a later time. More needs to be done for habitat assessment, especially in these urban areas within forested islands. And this graphic explains this really well to me. And also, we need to continue partnering with local stakeholders for sustainable conservation. Suksma, thank you. And we're very excited to continue working on this partnership together.